Morning, guys. Happy Wednesday. Today we're going to be talking about stoichiometric calculations, and so we'll be using some of the ratios that we were creating yesterday. Okay, so if you're following along with your book, this goes with page 358. Now, today, instead of making one long video that covers 3 different scenarios, today I'm going to make 3 short videos, each one covering a different scenario. Okay, so we're going to deal with mole to mole conversions, mole to mass, and mass to mass. But this video just focuses on mole to mole conversion, okay? So let's talk about how you use stoichiometry. Let's say that you have potassium and water. Now, those two things are very reactive when placed together, okay? And so let's say you are reacting potassium and water and you're going to produce pure hydrogen gas, okay? And you want to know how much hydrogen gas you're going to produce because, quite frankly, hydrogen gas is very dangerous, okay? And so you only know that you have 0.04 moles of potassium, and you want to know how much hydrogen gas. To solve the problem, you're going to use a mole to mole ratio, okay? So I'll write out the reaction for you. Let's say you have your balanced equation is going to be potassium plus water which is a liquid, and that is going to lead to potassium oxide. Sorry, not potassium oxide, potassium hydroxide, which is an aqueous acid, and hydrogen gas, which is H2. Okay, so this is your balanced equation. This is just balanced the way it needs to be so that we have the same number of potassiums on each side, the same number of hydrogens, so on and so forth. That's the only reason why this is balanced this way. But it does give us our ratios. So we are asking for how much hydrogen we're going to get if we know how much potassium we have. So what is the ratio of hydrogen to potassium? Well, we can use our coefficients for that, okay? So the coefficient of hydrogen is 1 because there's nothing there. The coefficient of potassium is 2. So our ratio is going to be 1 hydrogen for every 2 potassiums. Does that make sense? We've got 1 hydrogen for every 2 potassiums. Now we can use our mole ratio. Okay, so we are told in the problem that we are given 0.04 moles of potassium. Okay, so our given is 0.04 moles of potassium, and we want to know how much hydrogen gas. Okay, so we use our ratio, which now becomes a conversion factor. Okay, so we are given potassium, which means potassium needs to be on the bottom of the conversion factor to cancel out. So we have 0.04 moles of potassium times our conversion factor, 1 mole of hydrogen gas for every 2 moles of potassium. Essentially, we're dividing by 2. And so that's going to equal 0.02 moles of hydrogen to gas. Okay? And so if you put 0.04 moles of potassium into water, you are going to end up with 0.02 moles of hydrogen gas every single time. Okay? That's how that works. I'll go through one more example for you quickly. So this is the example problem on page 359 if you are following along in your book or if that is helpful to you. Okay? So let's say that we're talking about burning propane. Okay, and when we burn propane, which is C3H8, what you are going to yield carbon dioxide. Okay, and carbon dioxide is toxic. You shouldn't breathe it in, and that increases in its growing products. So the released carbon dioxide increases its concentration of CO2 into the atmosphere, which is bad. So we want to know how many moles of carbon dioxide are produced if you use 10 moles of propane. And that's burned excess in, let's say, an oxygen gas grill, which we use. Okay, so let's write down our knowns. I'll put this down here. Okay, so this is example problem number 2. We are given 10 moles of propane, which is C3H8. Okay, and we want to know how much carbon dioxide we get. Okay, so question mark, CO2. So first of all, we need our equation. So we know that this reaction is a combination of propane plus oxygen gas. And this is going to yield carbon dioxide and water. Now, we need to make sure that our equation is balanced because right now we have 3 carbons on this side and only 1 carbon on this side. So let's balance it real quick. We have plenty of that. So we're going to need at least 3 carbon dioxides to balance all of that out. Figuring that out, we now know that we are going to have at least 6 oxygens. So we need at least 3 here, plus another 1 there. But over here we have 8 hydrogens. And so for balancing this, we need at least 4 of these. Okay? So now we have 8 hydrogens on both sides, 3 carbons on both sides. How many oxygens do we have total? 3 times 2 is 6, plus 4 times 1 plus 4. 6 plus 4 is 10. So that means we need 5 O2s. So this is our balanced equation that we are now working with. Okay, so now we can go back to the ratios. We want to know how much carbon dioxide is going to be produced per propane. And so our ratio that we're going to write out is 3 moles of carbon dioxide for every 1 mole of C3H8 or propane. Okay, this again comes from our coefficients. The coefficient of carbon dioxide is 3. The coefficient of propane is 1. Okay, so our ratio is for every 1 mole of propane, we're going to get 3 moles of carbon dioxide. But we weren't given 1 mole of propane. We were given 10 moles of propane. Okay, so now we need to use our conversion factor again. We were given 10 moles of C3H8. Multiply that by our conversion ratio we just found. 3 moles carbon dioxide over 1 mole propane. So essentially, we're taking 10, multiplying it by 3. We know that we are now going to get 30 moles of CO2. Okay? And that is your example of how to do a mole to mole conversion, and it will help you with the first section of your Junopod today.